In the last session we have seen what is natural convection and how to determine the convective heat transfer coefficient, etc. Now we will apply those principles to solve a few important problems on natural convection. First problem. A 6-meter long section of an 8-centimeter diameter horizontal hot water pipe passes through a large room whose temperature is at 20 degrees centigrade. If the outer surface of the temperature of the pipe is 70, determine the rate of heat loss from the pipe by natural convection. So you can observe that there is no velocity term involved in it. The pipe is 6 meters long and 8 centimeter diameter. The room is at 20 degrees and surface is at 70. You are asked to determine the heat loss. So it is a problem related to vertical cylinder under natural convection. So we assume steady state and air is an ideal gas, etc., etc. And the first step is to determine the film temperature. The film temperature is, horizontal hot water pipe, The first step is the film temperature. And that film temperature is a Ts plus T alpha by 2, which is 70 plus 20 by 2, 45 degrees centigrade. So at this 45 degrees centigrade, you have to extract the properties of room air. Thermal conductivity, Prandtl number, V, etc. are taken, and beta is 1 by Tf because air is treated as an ideal gas. The coefficient of volume expansion is 1 by film temperature in Kelvin. So it is 273 plus 45, 380 in Kelvin. When it is a horizontal cylinder, the characteristic length is the diameter of the cylinder, which is given as 0.8, not 8 meters. So we calculate the Rayleigh number based on diameter as G beta delta T, that is Ts minus T alpha, d cube by nu square into Prandtl number. G beta delta T d cube by nu square into Prandtl number. We will get 1.869 in 10 power 6. So the flow is laminar. And for that laminar condition, the Nusselt number in this case is determined by using this equation. Or the range is given for Rayleigh number. In that range, when it falls, you can use this Nusselt number equation. So by means of this equation, you will get the Nusselt number, which is nothing but Hd by K. So H is equal to K by D Nusselt number. So that is equal to 5.86 watt per meter square degrees centigrade. And now the surface area of the pipe is pi dl. So pi into 0.08 into 6, 1.50, 8 meters square. And Q is equal to HA delta T, that is H is 5.869, surface area is pi dl, delta T is 70 minus 20, which is equal to 443 watts. So if you look at this pipe problem, because of its horizontal position, it loses only 443 watts and the Rayleigh number became very less, around 10 power 6. Instead, if you keep the 6-meter pipe in vertical position, the characteristic dimension becomes the length or the height, which is equal to 6 meters instead of 8 centimeters, and therefore the Rayleigh number shoots up like anything and it becomes turbulent, and thereby the H value becomes very high and rate of heat transfer is also very high. So that is the reason why in most of the power plants, the steam carrying pipes or hot oil pipes, when it is required to reduce the heat loss by means of natural convection, they are made to run in horizontal direction rather than in vertical direction. So in horizontal direction, a pipe convects naturally less amount of heat when compared to its vertical position, because the flow will never turn turbulent in laminar condition. The turbulent in case of horizontal position. And one more observation is the temperature of the body here is given as 70 degrees. So if you take into account the radiation factor from this, assuming emissivity of the pipe surface as epsilon 1, you can use the formula epsilon as sigma ts to the power minus ts power 4 minus t alpha to the power 4, that is Stefan Boltzmann law. You will work out it to be 553 watts. See that the 443 watts is by means of convection, and by means of radiation you have 553 watts. So this amount of heat loss by means of radiation in a natural convection manner, when it is considered, is not negligible. Hence the total heat loss we have to consider. So therefore this is much larger than the natural convection, and we have considered emissivity 1, but most of the real surfaces do not have emissivity 1, much less. So therefore maybe it becomes a little low, but anyhow radiation is still significant in most of the systems where the cooling is done naturally. Hence radiation analysis should normally accompany a natural convection analysis unless the emissivity of the surface is low. I hope it is clear to all of you. Let us move to the second problem. Take a square plate 0.6 by 0.6 meters, thin plate, so side areas are negligible, only face areas, two face areas, 0.6 meters square and 0.6 into 0.36 meters square on both sides at 30 degrees centigrade. The plate is maintained at 90 degrees centigrade and the other surface of the plate is insulated. Now determine the rate of heat transfer by natural convection if the plate is vertical, horizontal, facing up, the hot surface facing up, and horizontal hot surface facing down. The very important application oriented problem. Let us quickly T by 2, 60 degrees. We'll take K value, Prandtl number, nu value, and beta of course is 1 by Tf because air is treated as ideal gas. So 1 by 333 Kelvin. Now these are the positions: vertical, hot surface facing up, hot surface facing down. Perhaps it is more appropriate here, and concentrate and listen. Compare these two cases. Hot surface facing up. Air molecules on the upper surface gets heated up. Their density decreases because volume increases. Then buoyant force acts. They move up. That place is occupied by another molecule. Same hot plate surface facing down. A molecule attached to this surface, because it is hot surface, it also gets heated up. It loses its density. Then it will try to move upwards against gravity. It will never come down. So it won't vacate its position, and it will not allow another cold molecule to take its position and absorb heat from the hot plate. Hence the heat transfer rate when the hot surface is facing downwards is less when compared to the hot surface facing up. Approximately this will be 50% up. And for these horizontal positions, the characteristic dimension is surface area by perimeter. Whereas for a vertical position, the characteristic dimension is length or height of the plate. So take case by case. First, vertical plate, the characteristic dimension is 0.6 meters. Rayleigh number is calculated, Grashof number into Prandtl number. Grashof number is G beta delta T L cube by nu square. So the L is 0.6 nu square, you will get 7.656 into 10 power 8. And now let us choose the Nusselt number equation corresponding to that. You will get 113.4. Of course, we need not stick to this equation only. There are other equations available which will satisfy these conditions. Another simple equation is Nusselt number equal to 0.59 Rayleigh number to the power 1 by 4. If you carefully look, the answer which we have obtained using this equation and this equation are different, and in this case it is 13% lower. Anyway, it doesn't matter. Most of these are empirical correlations only. Variations will be there from one correlation to another correlation, and sometimes they may go up to 20% also. So once you decide Nusselt number as 113.4, H is equal to K by D Nu, and you will get the H value 5.306 watts. Here again the D means L only, characteristic dimension 0.6 meters, and surface area is 0.6 meters square into 0.36 meters square, and Q is equal to 115 watts. So when we keep the plate in vertical direction, it loses a heat of 150 watts. Now let us see what happens when I keep the plate in horizontal direction with its hot surface facing up. Now when it is in horizontal position, the characteristic dimension is LC equal to AS by P, surface area L square and perimeter 4L, you will get L by 4, 0.15 meters. And hence Rayleigh number is again G beta delta T L cube by nu square, 1.196 into 10 power 10. And we will use the equation Nusselt number equal to 0.54 Rayleigh number to the power 1 by 4, which is equal to 31.76. And we calculate H using the formula Nusselt number is HLC by K. We get 5.946, and surface area is 0.36 meters square, and you will get Q equal to 128.4 watts. So in case of horizontal position, its face, with its hot face facing upwards, you will get more heat loss, which is equal to 128.4 watts. Now let us see horizontal face, horizontal plate with its hot surface facing down. Because it is in horizontal position, the characteristic length remains same, Rayleigh number also same, but Nusselt number is used differently. That is 0.54 Rayleigh number to the power 1 by 4. This is 0.27 Rayleigh number to the power 1 by 4. And you will get the H value half of it, 2.973. And because surface area is 0.36, Q value will be 64.2 watts. So remember, natural convection heat transfer is lowest in the case of hot surface facing down. So it cannot get away from that plate easily. As a result, the cold air will have difficulty in reaching the plate, which results in reduced rate of heat transfer. Let us go to vertical pipe arrangement. We have seen horizontal cylinder, first problem. Then three positions of the plate we have seen. And now we will take up a problem on vertical pipe. This is also interesting and very application oriented. A vertical pipe of 15 centimeter dia, 3 meter long, surface is maintained at 100 and room area is at 20. You are asked to determine the heat loss from the pipe when it is 3 meters long, if it is 1 meter long, and if it is 50 centimeter long. So see, let us see the solution. Film temperature is 60, 100 plus 20 by 2. Properties are extracted, Prandtl number, thermal conductivity, mu. And of course beta is 1 by Tf. So this is equal to 273 plus 60, 333. And Grashof number is G beta delta T, vertical pipe. So characteristic dimension is length 3 meters, 3 cube by mu square, which we have obtained. And now Rayleigh number is the product of Grashof number and Prandtl number, that is 12.25 into 10 power 10. The condition to use that equation for vertical pipe is, we consider it as a vertical plate only, provided the D by L value should be greater than 35 by Grashof number to the power 0.2. So it satisfies that condition. Hence we will use the equation Nusselt number equal to 0.1 Rayleigh number to the power 1 by 3. You will get the answer 488. So from this, the convective transfer coefficient H is calculated as Nusselt number into L by K. That is 4.71 watt per meter square Kelvin. Into pi, I mean the determination of heat transfer is HA delta T, where A is the total surface area of the pipe, pi dl, pi into diameter is 15 10 power minus 2, L is 3 meters, delta T. You will get 532.6 watts if the pipe is 3 meter long. Now let us take the second case of 1 meter long. Again, let us check D by L greater than 0.12. It is satisfying, it is valid, hence we use the same equation, but in the case the LC is not 3 meters, now it is only 1 meter, so 6.55 into 10 power 9, and Nusselt number equation is same, 0.1 Rayleigh number to the power 1 by 3, it is 165.68, and H value is 4.798, whereas here it is 4.71. So Q is HA delta T equal to 180.8 watts. When I multiply with 180.8 with 3, it is going to be 540, whereas here the Q is roughly 532, more or less okay. But you will see a lot of difference if the pipe is 50 centimeter long. So third case, 50 centimeter long, D by L 35 by Grashof number 0.25, D by L is 0.3, and whereas this is 0.207, hence it is not satisfied. You have to go for a separate change. Let us calculate Grashof number taking LC as 0.5. You will get 8.12 into 10 power 8. Prandtl number 0.696. So you calculate Rayleigh number, that is multiplying Grashof number into Prandtl number, you will get the Rayleigh number. So this is laminar. You can observe carefully in the first two cases the Rayleigh number is very high. Grashof number itself is 10 power 10, and here also it is more than 10 power 9, but in the third case it is observed that the Rayleigh number is less than 10 power 9, and hence it is a laminar flow. So the equation to determine the heat transfer coefficient for laminar flow is Nusselt number is 0.59, Rayleigh number to the power 0.25. So you will get H value 5.27 and Q value 99.5 watts, 100 watts roughly. So three different cases where the characteristic dimension is considered as length of that piece. So if you consider a 3 meter long pipe or a 50 centimeter pipe, if you consider a 50 centimeter pipe, the heat transfer rate is 99.5 watts. So if you have 6 vents like that, the total heat transfer becomes 600 watts. Whereas for a single 3 meter pipe, it is only around 530 watts. So judiciously we have to identify in which position the plates, the pipe should be placed to minimize the heat loss by means of natural convection. Let us go to the another problem 4. Again, a steam carrying pipe of 20 centimeter dia, surface is maintained at 160, is in horizontal position, exposed to surrounding air at 20. Calculate the heat loss from the pipe per meter length. First calculate film temperature, that is 160 plus 20 by 2, 90. Then choose the properties at 90 degrees centigrade from the tables, and then calculate Grashof number G beta delta T L cube by nu square, and then calculate Rayleigh number, the product of Grashof number into Rayleigh Prandtl number. This is less than 10 power 9 and hence a laminar flow. So the equation which you can use is root Nusselt number equal to 0.6 plus 0.387 Rayleigh number to the power 1 by 6 by 1 plus 0.559 Prandtl number to the power 9 by 16 whole to the power 8 by 27. That gives you Nusselt number equal to 47.74. Because the characteristic dimension here is the diameter of the pipe because it is in horizontal position. So H value is determined by using the Nusselt number into K by D. So you got 7.46 watt per meter square Kelvin. Hence Q equal to HA delta T, where A is the pi dl per meter length we are assuming, and that is given from the meter length. You will get the answer as 650 watts. So before closing this session on natural convection, like we have seen the step-by-step procedure in forced convection, I will brief the step-by-step procedure in natural convection also. The first step is identify whether the problem belongs to natural or not. If velocity of fluid or mass flow rate is given, it belongs to forced convection, otherwise it is natural convection. Identify the fluid, whether it is air, water or some other thing, etc. And then calculate the film temperature. Tf is equal to Tw plus T alpha by 2, and then choose the property set there. Next step is identify whether the body is a plate or cylinder or sphere. If it is a plate, you have 3 positions: horizontal, vertical or inclined. For horizontal plates, the characteristic length is surface area by perimeter. For vertical or inclined length, the characteristic dimension is height of the plate. If it is a cylinder, again verify whether it is in horizontal position or vertical position. And for horizontal position, the characteristic length is diameter, and for vertical position, the characteristic length is length of the cylinder. And for sphere, the characteristic dimension, obviously the diameter of it. Grashof number is the ratio of inertia force to viscous force into buoyant force by viscous force. Calculate that Grashof number, then calculate the Rayleigh number by multiplying that Grashof number with Prandtl number. If Rayleigh number is less than 10 power 9, it is laminar. If Rayleigh number is greater than 10 power 9, it is turbulent. Now, after establishing the flow is laminar or turbulent, go to the relevant equation from the table. considering whether it is laminar or turbulent, constant wall temperature or constant heat flux. For horizontal position, heated face up or heating face down, etc. Then calculate Nusselt number. H is equal to Nusselt number into K by LC, and you will get Q equal to HES into TW minus T alpha. So that is about the natural convection in an overall manner. It is not that much complicated as forced convection, because in forced you have both external and internal. In natural there is nothing like internal or external. It is a surface phenomena which occurs. Even in cavities also it can happen, but as an undergraduate course we are not going in detail into those cavities, enclosed spaces, and combined natural and forced and free convection, etc. We limit ourselves to this discussion. Now we have finished the forced convection, external flow, internal flow, and natural convection. So let us quickly take some review questions, try to answer these questions, otherwise I will provide the answers in the coming sessions. Will a thermal boundary layer develop in flow over a surface even if both the fluid and surface are at the same temperature? Next, how does turbulent flow differ from laminar? For which flow is the heat transfer coefficient higher? What is the physical mechanism that causes the friction factor to be higher in turbulent flow? What is turbulent thermal conductivity? What is it caused by? Is the acceleration of fluid particle necessarily zero in steady flow? Explain. For steady two-dimensional flow, what are the boundary layer as approximations? This question number 53 is very important. Steady flow, is the acceleration is zero? Think and then try to answer that 53 question, very important. What are the advantages of non-dimensionalizing the convection equation? And now these questions are from forced convection. What is the difference between upstream velocity and the free stream velocity? For what type of flows are these two velocities equal to each other? What is drag? What causes it? Why do we usually try to minimize it? Next, consider laminar flow over a flat plate. Will the friction coefficient change with distance from the leading edge? And how about the heat transfer? How are the average friction and heat transfer coefficients determined in flow over a flat plate? And coming to natural convection. What is natural convection? How does it differ from force? What forces cause natural convection? Consider a hard-boiled egg in spacecraft that is filled with air at atmospheric pressure and temperature at all times. Will the egg cool faster or slower when the spacecraft in space instead of on the ground? Explain. When will the hull of a ship sink in water deeper? When the ship is sailing in fresh water or in sea water? Why? This question, of course, though not connected to directly to heat transfer, it is related to buoyancy. So if you understand this question, to a certain extent you can understand the natural convective phenomena. Consider a fluid whose volume does not change with temperature at constant pressure. What can you say about natural convection heat transfer in this medium? Very interesting. Show that the volume expansion coefficient of an ideal gas is so and so. How does the Rayleigh number differ from Grashof number? Under what conditions can the outer surface of a vertical cylinder be treated as vertical plate in natural convection calculations? That relationship is given. Look at it. Will a hot horizontal plate whose backside is insulated cool faster or slower when its hot surface is facing down instead of up? This question, if you are able to answer, you will get the knowledge why in all the refrigerators the deep freezer is located at the top of the refrigerator. The deep freezer is the coldest body which is located at the top of the refrigerator, inside the refrigerator. Because when cold body is at the top, molecules attached to it lose their temperature, volume decreases, density increases. So the density increment in addition to the gravity will make them to flow downwards more effectively. So natural convection currents will set up effectively when you keep that deep freezer at the top position in the refrigerator box, so that the contents which we place even at the bottom get cooled effectively. Instead, if you keep the deep freezer at the bottom, cold air will not move up because it is denser than hot air. So uniform distribution of cooling is not possible in the refrigerator. Anyhow, you try to answer. When in natural convection negligible, when is natural convection negligible, and when is it not negligible in forced convection heat transfer? Under what conditions does natural convection enhance forced convection, and under what conditions does it hurt forced convection? When neither natural nor forced convection is negligible, is it correct to calculate each independently and add them to determine the total convective heat transfer? Think over, otherwise the next session, at the end of the session, as usual, I will present the answers. I strongly advise you to go through these books. Convection particularly we have finished, but we have not gone through the derivations. Mathematical part is mostly omitted because it is only an undergraduate course. Anyhow, if you go through these, heat and mass transfer by Eunice S. Sengel or Frank Reed, in Cropera and Dewitt, or in my book to a certain extent, you will find all the derivations necessary for understanding the mathematical modeling of a convective system. Okay, thank you very much.